Welcome to a new course. In this course, we will cover machine learning with Python's Scikit-learn library. Let's start with basics of machine learning. So there's two types of machine learning, supervised and unsupervised. In the supervised machine learning, we have features like x1, x2, x3, and we have a label. So think this like we have 2 as the x1, 3, 4, and our label is 8. We are predicting this y with these features, so we have label in supervised learning. In unsupervised learning, we have x1, x2 features, but this time we don't have a label. Like we have 1 and 2 in here, but we don't have any more information. So think this unsupervised learning thing like we have features in here and features in here, and this is just like a grouping thing. But in the supervised learning, we know the true values, so we can train models and we can make predictions. Also, we can make predictions on the unsupervised learning side too, but we will never know how good is our predictions. But in the supervised learning, we can test our models like think it like we have 100 data points and we can train our model on 80% of the data and we can test the performance on the 20% of the data. This is also referred as train test split, and we will also cover that in the course. And in the supervised learning side, there is different things like we will look at two problem types, regression and classification. So, what are them? In the regression side, we are just going to see problems like our y variable, our target, is going to be continuous, like it can be 30, 3000, and we are just going to predict this like we are going to have a line like this. It doesn't need to be in a linear form. Also, it doesn't need to be a line, but just for the concept. And we are going to have the features and we are going to have the label. With this line, let's assume that we are going to predict this point. But in the classification side, we are going to have classes like our y variable is going to be something like 1, 0, maybe 2. And how this is going to look like is I'm just going to show you the graph of the logistic regression. Our y and x is going to be in here, and for the y, let's say the output is going to 0 or 1, and here is the logistic regression line, and we are going to make predictions with these x values on unseen data, and we are going to get classes like 1 and 0. Like think this like let's give it a real world example on this too. Like at the regression side, we can just predict the salary someone is earning based on their education. Like if the education is 8 years, then the salary is going to be 40,000, and if the education is 12 years, then the salary is going to be 60,000. And at the classification side, what we can say is we can predict the sickness based on blood values, like let's say blood test value, and let's say this value is 10, so we are going to say sick, and if it's 5, then we are going to say not sick, and we can use classification like this. So let's start coding. We will use Scikit-learn for applying the machine learning models. First things first, make sure you have Python installed. If not, you can download it from python.org. Once that's done, you can install Scikit-learn library using pip. Like you can open the terminal and you can say pip3 install Scikit-learn. Also pip works sometimes. Actually it's like install scikit and we need this. And we have the Scikit-learn right now. Also sometimes pip3 won't work and you can just go with pip install scikit-learn and this will work. Great! Now we will get a dataset to work with. I'm going to use the datasets which comes with Scikit-learn library. Let's use iris. We will use different dataset too in this course. So what we are going to do is we will say from Scikit-learn.datasets import load iris, and after that we are going to say iris, and we will use load iris method, and we will set the data like iris.data, and we are going to set the target like iris.target. And what else we can do right now is we can just check if they are installed successfully, like you are going to see array like this, and at the target side you are going to see a similar thing. And from this we can understand that our target y is like the classes 0, 1, 2, so we have a classification problem at the side. Now let's understand the structure of this dataset. So what we can do is, let's say print feature names, and what we are going to say is iris.feature names. There's information about flowers, I guess, and let's say print target name, and we will say iris.target names, and target names are these classes. Like, I'm not sure what are they, but think this like if it's 1, I'm just giving an example, it's verse color, and if it's 0, it's setosa, and etc. And let's see our data shape. So what we are going to do is we will say print data shape, and we will say data.shape after that. So this means that we have 150 rows and 4 columns in our data at the X side. Great. Now we are going to talk about techniques for data preprocessing. This is a pivotal stage in any machine learning project, and Scikit-learn provides us with powerful tools to make this process seamless. So let's firstly convert our data frame to a pandas data frame for better visualization. So what we can say is, also we need to import pandas firstly, and then what we are going to say is data frame is going to be equal to the pandas.dataframe, and we will say data and columns are going to be equal to the iris feature names. But if you run like this, you are going to see that your data frame won't have the target. So what we are going to do is we are going to set the target as target, and then when we call our data frame, we are going to see that our data frame seems nice. Great, let's jump into some common preprocessing techniques. We will cover cleaning, normalization, and feature scaling. So what if we want to check for missing values? We are going to do dataframe.isNull, and we will use .sum after that, and we don't have any values in here. So now let's cover normalization. We will say from Scikit-learn.preprocessing import min max scalar, and what we are going to do is we are going to initialize this scalar equals to min max scalar class, and we are going to say normalized data is going to be equal to the scalar.fit and transform data. So remember, data was our X features, and when we call them again, you are going to see they are going to be different from this normalized data. Like we have values like 7, 6, and if I call normalized data right now, you are going to see all the values are going to be scaled, and we have such low values in here. So this is a really common thing if you have different scaled values in your X. Like at one side you can have salary like 70,000, 80,000, and you can just have a car option at the X side, and their labels is going to be like 1 and 0. So at one side there is 80,000, at one side there is 1 and 0. So you need to scale your data before training your model. So now we are going to cover feature scaling. For that we will say from Scikit-learn.preprocessing import standard scalar, and we are going to initialize this like scalar is going to be standard scalar, and we are going to say scaled data is going to be scalar, and we will use the fit transform method again, and we will pass the data. So when we call our scaled data, you are going to see the values are going to be really low, and they are going to differ from the original X values. Great. Normally we do all the scaling operations after splitting our data for getting rid of data leakage, and we are going to cover train test split right now. Remember we talked about it, like we are going to separate our data. We will put some data in the training set and we will put some in the testing set. So we are going to have the chance to evaluate our model. Train test split is crucial for building models that generalize well to new unseen data. So how we do that is, we are going to say from Scikit-learn.model selection import train test split, and we will say xtrain, xtest, ytrain, ytest is going to be train test split. We will say data, target, and we are going to set the test size, like it's going to be the percentage which is going to be in the testing data, like the 20% of the data is going to be in our testing set right now. This 20% is a really common value, you can use that. And if we check xtrain shape right now, we are going to see we are going to have 120 rows in our xtrain, and also we are going to have the same in the ytrain. And if you check xtest, like xtest.shape, you are going to see we are going to have 30, and at the ytest we are going to have 30. Now, why we do this? Well, by splitting our dataset into a training set and a testing set, we can train our model on one set and evaluate its performance on another. This helps us ensure that our model doesn't just memorize the training data, but can generalize well to near unseen data. Now we are diving deep into the evaluation of classification models. It's not just about accuracy that you're going to see a lot when you are creating machine learning models. We are going to explore precision, recall, F1 score, and the confusion metrics. I'm going to use a k-neighbors classifier model for showing the metrics. We'll cover this model later in the course. I'm also going to do same type of section for the regression side, but don't worry, we are going to cover this model thing, .fit command, .predict command in the modeling side. For now, I'm just going to show you this because you are going to understand this model performances on the modeling side of the course, and I think this path will be better for the learning machine learning. So let's start by importing the libraries that we are going to use in this section. So I will say from Scikit-learn.metrics, we are going to import our evaluation metrics from here for both regression and classification problems. And then I will say import accuracy score, precision score. I'm going to explain all of them with simple sentences, but I have a full video about them. You can just check it for learning about them more. I will import recall score, F1 score, and confusion metrics. And then I'm going to import the example model. I will say from Scikit-learn.neighbors import k-neighbors classifier. And then after the imports, I will say knn, and I'm going to initialize the model class. I will say k-nearest neighbors classifier, and let's say number of neighbors equals to 2. And then I will say knn.fit, and I'm going to fit this model into a training set. And then using this model, I'm going to make predictions on the test set with using .predict. I'm going to make the predictions based on xtest, and I will compare the performances with ytest. So I will say predictions is going to be equal to the knn.predict xtest, and if we just check predictions, you are going to see it's an array which have our values. So we can understand from this too that with this xtest's first row, like with this, our model predicted this class 2. So now we can get our evaluation metrics. So for at the accuracy side, I will say accuracy score, ytest, and predictions. So here are our predictions, and it's just going to look with the ytest. It's going to compare, like we predicted 2, but the origin 1 was 1, so it's a wrong prediction, and it's going to give us the model success, like how well this model works on unseen data. We can think it like that. Accuracy measures the overall correctness of the model. So the next step is precision. So how we can get this is we are just going to say precision score. We are going to give y-test and predictions, and we are going to say average equals to weighted. And so precision indicates the proportion of true positive predictions out of the total predicted positives. So now we are going to talk about recall. I will say recall score, and we are going to give y-test, predictions, and let's give average as weighted. And we are going to see our recall score. By the way, they are coming AQ like 0.9333, but in the real world it's not going to be like that, and each of them have a different use type. Recall measures the proportion of true positives out of the total actual positives. So we will check F1 score right now, and we will give y-test, predictions, and let's get the average as weighted. And we can define this as a balance between precision and recall. At the last step, we are going to see the confusion matrix like confusion matrix, and we will give y-test and predictions. And we are going to see an array like that for the true positives, true negatives, false positives, and false negatives. All of the upper metrics are calculated from these confusion matrix. Great. Now we are shifting our focus to regression models and how to evaluate their performance. We will be covering mean squared error and R-squared. We will be still using the iris dataset, but this time we will select our label differently, which will make us predict continuous values with our model. Like now, let's check the y. It's something like 1, 2, 1, 0, and we are just going to try to predict some of these values. Like we are going to select a y from this x values, and we are going to create our regression model on this. I will use a linear regression model. We will cover this model later on the course. So what I'm going to do is I'm going to say from Scikit-learn.linear model import linear regression, and from Scikit-learn.matrix this time we are going to import regression metrics like mean squared error and R-squared score. Great. So this time we are going to recreate our dataset like iris is going to be equal to the load iris, and we are going to set data as iris.data, and then we are going to do y is going to be equal to the data, and we will do this filtering. Like you are going to see right now the y, it's the sepal length, and you can see we have values like 5.1, 4.7 instead of classes like 0, 1, and 2. So we are going to work on a regression problem right now. And we need to update our x-train, x-test, y-train, and y-test. And we will use train, test, split, and we will say data and y, and we will say test size equals to 0.2. And great. So at the y side, like y-test and y-train, we have the continuous values right now. Like you can just check y-train 2, and we are going to have a similar thing. Great. Let's create our regression model. Like regression model is going to be equal to the linear regression class. We are going to initialize this, and then I'm going to do regression model.fit, and I will use the training data we have. And at the next step, we are going to do predictions with this, like regression model.predict x-test again, and these are our predictions, and now we are going to compare them with y-test. So what I'm going to do is I'm going to save these predictions like regression model.predict x-test, and at the next step we can use our evaluation metrics. So let's start with mean squared error. So we will say mean squared error, and we are going to say y-test and predictions. And now we are going to see our mean squared error. At the mean squared error side, it's better to be this value is lower. Like if it's lower, your model is better. Mean squared error measures the average squared difference between the predicted and actual values. Remember that actual values are the y-test and predicted ones are the predictions. Lower values indicate better performance, as I just said. So let's just use r squared, like r squared score, and we'll say y-test and predictions. And what is r squared is, by the way, it takes value between 0 and 1. It's just like impossible in the real world scenarios, like r squared can't be this good, but it's just an example dataset. And what r squared is? R squared represents the proportion of the variance in the dependent variable that is predictable from the independent variables. It's not like mean squared error. A higher r squared indicates a better fit. Great, now we can start to learn the machine learning models. We will start with classification models and keep with regression models. And then we are just going to look at the unsupervised learning side. We will start with k-nearest neighbors, a powerful algorithm for classifying data based on its proximity to other data points. We already imported it in the example data, example classification matrix side, and I'm just going to re-import it because we are just going to learn modeling and it's better to remember this, I guess. I will say from sklearn.neighbors import k-nearest neighbors classifier. And we are going to reload the dataset since it's set for the regression problem. I will say iris equals to load iris, and I will say data equals to iris.data and target equals to iris.target. And our target is going to be like 0, 1, 2 again, like you can see from here. And we are going to redo the train test split. It's better to do this again because you are going to see this a lot, because if you are training a machine learning model, you need to know how well it performs. So I will say train test split, data target and test size is going to be equal to 0.3 for now. By the way, setting this to 0.3, it means that in the training side of our dataset, there's going to be the 70% of the total data, and at the test we are going to have the 30%. Great. By the way, at the modeling side we have parameters for all the models, and in this course we are going to look for them and how we can optimize this model's performance by hyperparameter tuning, and I'm going to teach it also. Great, let's initialize our KNN classifier. So KNN is going to be equal to the k-neighbors classifier, and then we are going to fit this into our training data like x-train, y-train, and we are going to make predictions with that. So we will say predictions equals to knn.predict, and we will use x-test, and we can just get accuracy. It's the most common one, so we will say accuracy score and y-test with predictions. Great. The KNN algorithm classifies a data point based on the majority class of its k-nearest neighbors. The value of k is crucial hyperparameter that we'll explore in a second. Let's talk about hyperparameter tuning again. Hyperparameter tuning involves optimizing the settings of a machine learning model that are not learned from the training data but set prior to the training process. These settings, known as hyperparameters, they have significantly impact the model's performance, and the tuning process typically employs techniques like grid search or random search to find the best combination of hyperparameter values, enhancing the model's effectiveness on unseen data. Hyperparameter tuning is crucial for achieving optimal model performance and generalization across different datasets. We will cover hyperparameter tuning steps for every model in this course once again. Now we will focus on finding the optimal value for the hyperparameter k in KNN algorithm. This step is crucial for fine-tuning our KNN model and achieving the best possible performance. So what we are going to do is, let's just initialize our model again, like KNN is going to be equal to k-neighbors classifier, and we are going to define the parameters that it can take. Like we are just going to say param grid, and it's the most common usage, you can just use it like that, and we are going to use a dictionary. For each parameter, you will say the keys and values like this, and we are going to give 1 to 30, and we are just saying our grid search that you are going to look for these values one by one and find the best performing one. If we were going to add a different parameter than this, we are just going to say a, and it can be like list of strings like 1 2 3 but or abc, but we are just going to cover that because other models have parameters like this. At the KNN side we won't need that, and now we are going to import the grid search. So I will say from Scikit-learn.model selection import grid search cross-validation, and what we are going to do is we are going to initialize this like grid search. We will say grid search cross-validation, and we will give the model firstly, and then we are going to give our parameters. And by the way, we need equal sign after this. I made a typo. And then we are going to say cross-validation, like we can just set this to 2, and I'm just going to explain it in a second. This CV cross-validation is a resampling method used to test the model's generalization ability using out of the sample data chunks. So I'm just going to run this, and what I'm going to do right now is I'm just going to use this grid search, and I will use the fit method, like fitting the base models, and we will use xtrain and ytrain. And after that, this process, we can just get the best parameters for every model, like grid search best parameters and underscore also, and we are going to see number of neighbors 7 was the best performing one. Also we can make predictions with grid search object like predict, but I'm just going to show you different thing. I will say best parameters, and I'm going to say number of neighbors, and after that we are going to get this 7 in here, and I'm just going to set this as best k. And then what I'm going to do is I will say best KNN, and I will recreate model like k neighbors classifier, and I will set the number of neighbors to the best k. And I'm going to create this model like this, and I'm just going to fit this using my training data. We will train this model xtrain, ytrain, and after that I will get the predictions best knn.predict xtest, and let's get the accuracy score in here, like accuracy equals to accuracy score ytest and predictions, and let's just call the accuracy in here, and we are going to see it's 0.905. So accuracies remain same because it's an example dataset. In the real world scenarios, your model performance will increase this with this grid search, and 0.95 is a really high accuracy, and you will get better performing models if you use grid search. And we are going to cover this method for every single model that we are going to cover in this course. Okay, let me just repeat. Grid search cross-validation search through a specified parameter grid, in this case different values of k, and evaluates their performance using cross-validation. The result is the best parameter value that maximizes model performance. Now we are shifting our focus to another powerful classification technique, decision trees. Decision trees are intuitive, easy to understand, and capable of handling both numerical and categorical data. Algorithms like decision tree and random forest, called as tree-based methods, and we are going to say from Scikit-learn.tree import decision tree classifier, and then we will say data frame decision tree classifier is going to be equal to the decision tree classifier. We are going to initialize our model, then we are going to train the model on the training set. So I will say decision tree classifier that fit xtrain, ytrain, and after fitting our model we are going to do predictions with it. We will say data frame classifier. Actually I read the T like F, so why I called is as data frame it's decision tree, and we can just get our accuracy score like ytest and predictions. So our accuracy score is 0.93. Great. Decision trees work by splitting the data based on features, creating a tree-like structure. Each leaf node represents a class label. The depth of the tree and other hyperparameters play a crucial role on its performance. Now let's discuss parameter tuning for decision trees. We will focus on finding the optimal values for the tree depth and the splitting criterion. So I will say parameters grid, and I'm going to set this like max depth is going to be range 1 to 11, and then we are going to set the criterion as Gini and entropy. And now we are going to use grid search to find the optimal parameters, like grid search equals to grid search cross-validation, decision tree classifier, parameters grid, and let's set the cross-validation as 3. And then we will fit this to our training data. Actually, I need to use lowercase. I will say fit xtrain and ytrain. And now we can just check the best parameters, like grid search dot best parameters, and we are going to say best criterion is Gini and best max depth is 2. So what we are going to do, we are going to do a similar thing. I will say best depth, and it's going to be equal to the grid search dot best parameters, and we are going to take the value of the max depth. And after that, I will say best criterion, it's going to be equal to the grid search dot best parameters, and from here we will get the criterion. And now what we are going to do is we will say best decision tree classifier, and it's going to be equal to the decision tree classifier. Max depth is going to be equal to the best depth, and criterion is going to be equal to the best criterion. So after this, we are going to train this model with these parameters, like we will say dot fit xtrain and ytrain. After this step, we can make predictions with this model. Like what we can do is we can say predictions is going to be equal to the best decision tree classifier dot predict, and we will say x test. So after having our predictions, we will say accuracy score, y test, and predictions. And here is our accuracy score. It didn't change again since we are using an example dataset, but in the real world, you can improve your model performance like this. Now we are going to talk about random forests. Random forests are a powerful extension of decision trees, providing improved accuracy and robustness through the combination of multiple trees. Like you are having more decision trees than one, and you are going to make predictions based on their results. So let's just import it from Scikit-learn.tree, import random forest classifier. And after this, we will say random forest classifier is going to be equal to the random forest classifier. And after this, actually, there's a problem. I just checked, it's taken to the ensemble like this, and after doing this, maybe it was in the ensemble, the entire process of scikit-learn development, I'm not sure, I remember like 3. And after this, what we are going to do is we will say random forest classifier dot fit, and we are going to fit this using xtrain and ytrain. And after that, we are going to make predictions like random forest classifier dot predict x test, and we are going to get the accuracy again with y test and predictions. Great. Random forests work by constructing multiple decision trees during training and outputting the class that is the mate from that decision trees. It's the mode of the classes of the individual trees. Now let's discuss parameter tuning. For random forests, we will focus on finding the optimal values for the number of estimators, which we can also refer as trees, and the maximum depth of the trees. So we will define parameters grid, and we are going to create a dictionary. We will say number of estimators, and it's going to be like 50, 150, 200, 250, and then we can say for the max depth side, we can say none, 10, 20, and 30. And now we are going to use grid search. We will say grid search, and it's going to be equal to the grid search cross-validation, random forest classifier, parameters grid, and let's set the cross-validation as 3, and we are going to fit this using grid search, and training data we have white train, and after this we are going to do check the best parameters like best parameters, and max depth is 10 and the number of estimators is 200 at the best parameters side. So what we are going to do right now is let's set best estimators as grid search dot best parameters, and we are going to take the number of estimators from here, and I'm just going to make copy paste because you already know the process. And what we are going to do in here is we will say best depth, and it's going to be best depth, max depth. Great. So we will create something like best random forest classifier, and it's going to be random forest classifier number of estimators is going to be equal to the best estimators, and max depth is going to be equal to the best depth, and that's it. We are going to train this model right now. Best random forest classifier dot fit x train and y train. So what we are going to do right now is we are going to make predictions with this. Predictions is going to be equal to the best random forest classifier dot predict x test, and after that, actually I made a typo, x test, and after that we are going to get our accuracy score predictions. Actually there's a problem, let me quickly check. Actually I need to give also the y test, and after that it's going to work smoothly. Here it is. Great, now we are going to talk about support vector machines. Support vector machines work by finding the hyperplane that best separates different classes. This hyperplane is chosen to maximize the margin between classes. It's great for both linear and non-linear datasets. So what we are going to do is I will say from Scikit-learn.svm support vector machines import support vector classifier like this. And after that we will initialize this like svm classifier is going to be equal to the support vector classifier, and then we will say svm classifier that fit, and we are going to fit this into our training data, like we are going to train the model, and after that we will store the predictions which we are going to make with this model in predictions variable, and after that we are going to do accuracy score, y test, and predictions. Great, 0.95. Okay, we were talking about a hyperplane. This hyperplane is chosen to maximize the margin between classes again. Now let's discuss parameter tuning for SVM. We will focus on finding the optimal values for the kernel. It can be linear, polynomial, or radial basis function, and the regularization parameter C. So we are going to create parameters grid, and this time it's for support vector machines. We will say kernel, and it can take values like linear, poly, and RBF. And for the regularization parameter, we are going to say 0.1, 1, 10, and 100. Great. Now we are going to use grid search again. We will say grid search, and it's going to be equal to the grid search cross-validation support vector machines classifier parameters grid, and let's just set cross-validation as 3, and we are going to say grid search that fit x train and y train. I'm going to correct my typo like grid search. Great. Now we have our model, and we can just check the best performing parameters like best parameters, and here it is. polynomial for kernel and 0.1 for C. Great. So what we are going to do is we are going to save this best parameter values like best kernel, and for just making this faster, I'm just going to do like this right now because we have the values, and for the best C side we will say polynomial. Great. It's same with writing grid search best parameters kernel and C. And now we will say best SVM classifier, and it's going to be equal to support vector classifier, and we are going to set our parameters like best kernel, and then we will say C is going to be equal to the best C. And now with this, what we can do is we can train our model SVM classifier that fits X train and Y train. And after that, actually there's a problem. Let me quickly check. The C parameter must be float. So I think I made a mistake, like kernel is going to be polynomial and C needs to be 0.1. I missed that, and now we can do just train our model without problems. Great. Now we are going to do predictions, like it's going to be equal to the best support vector meshes classifier that predict X test, and we can just get our accuracy score with Y test and predictions we made with this model, and it's 0.95. Great. Now we are delving into regression techniques with Scikit-learn, starting with one of the fundamental models, linear regression. Linear regression is a powerful tool for predicting numerical values based on a linear relationship between features. We will also switch to a new dataset. We will use a different one. There won't be parameter tuning part of the linear regression, but other regression methods we are going to have that. So let's just create our new dataset. Like we will say from Scikit-learn.datasets import load Boston, and after that we will say from Scikit-learn.linear model import linear regression. And actually there's a problem. Let me quickly check. It says load Boston has been removed from Scikit-learn, and what we can do right now is, so we can just try another dataset, like I found diabetes like this, and after this we can do like diabetes can be load diabetes, and after that data can be diabetes.data, and target can be diabetes.target, and after this we can just check target if it's a regression problem. Yes, it is. Great. So instead of Boston data, we are going to work with this diabetes data. Also, let's check the data side of things, and great, we have the values in here. So let's do the X train, X test splitting operation, Y train, and Y test is going to be equal to the train test split, and we will say data target. We are using the diabetes dataset. Let's use test size 0.2 this time, and let's just check this. Yes, we imported the linear regression, so we can directly use that. So what we are going to do is, let's say linear regression model is going to be linear regression class. Then we will say linear regression model.fit, and we will train this model with X train and Y train, and we are going to get predictions, like predictions is going to be equal to linear regression model.predict X test, and after that, after I correct the typo like this, let's just check the predictions. They are going to be continuous values. Like you can see, they are not like classes. And let's just get the mean squared error. We already imported it, and we will say Y test and predictions again. And here's our mean squared error. Also, let's get the R squared here, Y test and predictions. And here it is. Also remember that we want our score to be higher and mean squared error to be lower. Okay, now we are going to talk about ridge regression. Ridge regression is an extension of linear regression that includes regularization to prevent overfitting, which means that your model fits on your training data well, but it performs really bad on unseen data. It doesn't predict the unseen data. It just remembers what you did in training data, and it's just not useful in real life. Also, we have a parameter for this, and for the next models, we are going to have parameters, and we are going to do hyperparameter tuning. So for importing the ridge regression, we will say from Scikit-learn linear model import ridge. And after that, we are going to initialize this like ridge model is going to be equal to the ridge. And now we are going to train our ridge model with base parameters like ridge model.fit. We will use xtrain and ytrain. And after that, we are going to get our predictions with this base model like ridge model.predict x-test. So we can just get mean squared error like y-test and predictions, and we can get r-squared score with y-test and predictions. Great. So ridge regression introduces a regularization term controlled by the hyperparameter alpha, which helps prevent the model from fitting the noise in the training data. Now let's discuss parameter tuning for ridge regression using grid search. We will set our parameters like parameter grid is going to be equal to the alpha is going to be 0.1, 1, 10 and 100. So after that, we will say grid search is going to be equal to the grid search cross validation. We will say ridge model parameters grid and cross validation is going to be equal to 2. And now we are going to fit this into our training data, which means training the model, and we can just check the best parameters like grid search.best parameters, and you will see alpha 0.1 is the best performing one. So let's just set this like best alpha is going to be grid search.best parameters and alpha from here. And after that, we can just create best ridge model, and it's going to be ridge alpha equals to best alpha. And after that, we can train our model with this like best ridge model.fit xtrain ytrain, and we can just make predictions with this like predictions is going to be best ridge model, and we will give x-test in here. And actually there's a problem, let me quickly check. We need to use predict in here, and with that it's going to work. Great. So we can get our mean squared error in here like y-test and predictions, and we can get our r squared like y-test and predictions. Great. So actually I think, let me quickly check, with the base model we have 0.38 in r squared and we want it to be higher, and with the parameter tuned version we have 0.44. So we have an improvement in the model performance. Now we are going to talk about lasso regression. Lasso regression, like ridge regression, is a regularization technique that helps prevent overfitting and can perform feature selection. So we will say from Scikit-learn.linear model import lasso, and after that what we are going to do is we will say lasso model is going to be equal to lasso. We are going to initialize this, and after that we are going to fit this using our training data, and we are going to make predictions with that lasso model.predict x-test. And what we are going to do now is let's just get the r2 score and y-test and predictions. Also I need to add this in here. Great. Lasso regression adds a penalty term proportional to the absolute values of the coefficients. This can lead to some coefficients becoming exactly zero, effectively performing feature selection. Now let's discuss parameter tuning for lasso regression using grid search. We are going to say parameters grid, and we have the alpha parameter, and it can take values like 0.1, 1, 10 and 100. And what we are going to do right now is grid search cross validation, lasso model and parameters grid, and let's set the cross validation as 2. We will say grid search fit x train and y train. After that, we are going to get the best parameters like best parameters. Then let's set the best alpha, like best alpha is 0.1. Then we are going to create best lasso model. Lasso alpha is going to be equal to the best alpha. Then we are going to fit this like best lasso model dot fit x train and y train. Also, I want to show you something, that instead of doing this, retraining your model with the best value, you can just use this grid search and you can just use predict with this. It's going to be same, but since I'm teaching this, I'm just rewriting it every time for you to understand the models better. And after that, we are going to say predictions is going to be equal to the best lasso model dot predict and x test, and let's just get r squared for this y test and predictions, and we will get 0.43. The base model was 0.29, and in the regression problem we are seeing the improvement in the parameter tuning. Great. For the final regression technique, actually there's a lot more, but we are going to cover this one also since this is essential. We are going to talk about polynomial regression. Polynomial regression is a powerful technique that captures nonlinear relationships in the data by introducing polynomial features. Let's create a synthetic dataset for this. Like, I'm going to import NumPy and I'm going to import matplotlib also. I'm going to make a visualization on this, pyplot as plt, and we are going to import preprocessing, import polynomial features from here, and I'm just going to run this like this. And now what we are going to do is we will say x is going to be equal to the, let's say 6 multiplied by numpy random 100 1 minus 3, and for the y side we can say 0.5 multiplied by x with the power of 2, and after that plus x plus 2, and we can do plus numpy random, and we will say 101. Great. So let's just check the x. We have values like this, and let's just check the y. Great, we have the values like this. So I'm just going to split the data like x train, x test, y train, and y test, and I will use train test split x and y, and let's set the test size as 0.3. And now what we are going to do is we will say polynomial features is going to be equal to the polynomial features. We will say degree equals to 2, then let's say include bias false, and we will say x train polynomial, and we will use x train, and then we will say actually we need to use polynomial features, and we will use fit transform method, and I will say x train after that. And now what we can do is we can just check the difference between x train and x train polynomial like this, and you will see the difference right now, and great. So now I will set polynomial regression model, and I will say linear regression. After that I will say polynomial regression model that fit x train polynomial and y train. After this we can just check our model performance, but we need to do like x test polynomial, and it's going to be equal to polynomial features that transform, actually fit transform, and we need to say x test. After that we will say predictions equals to polynomial regression model dot predict x test polynomial. Great. Now we can just check our score like y-test and predictions, and we will see it's 0.87. Actually, I said like I'm going to visualize this, but I'm not going to do that. And now we are going to shift our focus to unsupervised learning, and our topic is going to be k-means clustering. It's going to be the most common unsupervised learning method you are going to see. K-means clustering is a popular clustering algorithm that partitions data into k-distinct non-overlapping subgroups, which we can also refer as clusters. Let's use a synthetic dataset for our hands-on demonstration. So what we are going to do right now is, actually I can use matplotlib. In here we will say from Scikit-learn.datasets we will import make blobs, and we will import from Scikit-learn.cluster import k-means, the algorithm we are going to use. So we will say x and y, we will set make blobs number of samples 300, and let's set the centers as 3. This is the form of the x, and now we can visualize this. So we will say plt matplotlib.scatter, and we will take x and 0 in here, then we will take x and 1 in here, and for the C side we will say y, then we will say cover map, and let's say this for the cover map, then let's set the edge color as k, and for the S we will say 50. I think it's edge color. If it's wrong I will just fix it. And let's say for the title side say synthetic dataset with clusters, and for the X label let's say feature 1, and for the Y label let's say feature 2, and we will use plt.show at the end, and here it is. So here we have 3 groups, and in our model we are going to group this, like for each color we are going to say they are going to be clusters, so we are going to set the number of clusters as 3, and by this we can make predictions like if a data point comes between the yellow and the green ones, we can just look which center it's more close to, and we can just label them like that. Like if it's closer to the yellow side, we can just say it's on the yellow cluster, it's in that class, it's on that cluster, and we can just classify it like this. So let's do that. We will say k-means model, and we are going to create our model like k-means, and we are going to set number of clusters as 3. Then it's it, I think. And now we are going to fit this like using .fit command again, but remember we don't have y in here, so we will say x, and then what we are going to do is we are going to set the cluster centers with k-means model.cluster centers, and we are going to set the labels like k-means model.labels. And after setting them, what we are going to do is we are going to visualize the clusters. So we are going to say plt scatter. Actually, let me copy the upper thing, the first line. I'm just going to copy this because I need to write the same thing. And after that, now I'm going to say plt scatter, and after that I will say cluster centers, and I'm going to do 0, and I will say cluster centers, and I will say 1. Let's set the color as red in here, and let's set the marker as x, and let's set the S as 200, and we will say label is going to be equal to the cluster centers. And then what we are going to do is we will say plt title k-means clustering results, and we are going to do x label feature 1, y label feature 2, and legend, and we will use plt.show at the end. And here it is. Great, you can see the centers. So based on the distance between these centers and the new data points, we can just move our new data to these clusters. Great. In this example, we have created a synthetic dataset with 3 distinct clusters and applied k-means clustering to identify these clusters. Now let's discuss the process of choosing the optimal number of clusters, often referred as the elbow method. So we are going to have a metric like inertia, and we can just call it like within cluster sum of squares. And what we are going to do is we will say define, calculate, we are going to create a function like this, inertia, and we will give the data inside and the maximum k inside. Then we are going to say inertias, and we will create an empty list. We will use append method after, and we will say for k in range 1 and maximum k plus 1, and we will say k-means model equals to k-means, then we will say number of clusters equals to k, and then we will fit this for every value in range 1 and maximum k plus 1, fit k-means model fit, and we will use data. Then we will say inertias append k-means model inertia, and we will return inertias at the end. Here it is. Okay, let's apply the elbow method now. We will say maximum clusters is going to be 10, and we will set inertias like calculate inertia. We will give x and maximum clusters, and here it is. So at the next step, we are going to visualize the elbow method like plt.plot range 1 to maximum clusters plus 1, and we will give inertias, and we are going to set the marker as O. Okay, then let's give the title like elbow method for optimal number of clusters, and we will set the x label like number of clusters, which we can also refer as k, and we will set y label as inertia, and we will use plt.show at the end, and here it is. From here we can select the k value based on the lowest inertia. Actually, after the tree, as you can see, there is no significant change. So if I was modeling on this graph, I will take the tree as the number of clusters because there is no significant change. There is no need to add new clusters. Actually, it really depends on the problem, but I'm just telling what I will generally do. You can take the point which is going to be changed, going to be smaller after that point, like from 3 to 10, the changes are really small, and I think there is no point and there's no difference on taking 10 bit and 3. Okay, for the final part of our course, we are going to talk about model persistence and serialization in Scikit-learn. Model persistence involves saving a trained machine learning model to a file so that it can be easily reloaded and used later without the need for retraining the model. So we are going to use joblib for that, and what we are going to do is let's load our iris dataset again and train a basic model. I'm just going to make a copy paste in here. Let me find the related code. I'm going to be in here in a second. Okay, for the iris load dataset side we will do this. And after that, what we are going to do is we are going to do train test split, as we've done a lot in the course, and we are going to train a random forest model with 100 number of estimators. And what we are going to do is actually we don't need to get the predictions and accuracy, but I'm just going to do that like accuracy score, y test, and predictions. And here we have our model. So now in the destination I don't have any files, and we are going to save this machine learning model as a pickle file. it's a special type for the Python files, and it's commonly used in the deployment of the machine learning models. Like what we can do is we are going to say model file name, and we can just name this like random forest model.joblab. And what we are going to do right now is we are going to say joblib.dump, we will say random forest model, and we will say model file name. And after doing this, you are going to see we have random forest model.joblib in here. Also, as I said, pickle file is really commonly used. You can just say pickle in here, and after saving this, you are going to get the pickle file in here. But we are going to move with the joblib extension right now, and here is our model. And how we can load this is we can say loaded model, and we are going to say joblib.load, and we are going to give this file name, just like reading CSV files in pandas data frames. And here it is, we loaded our model. And let's create a new data point for the prediction side. Like think this, your customer wants to get a prediction. You'll say 3.5, let's say 1.4 and 0.2. And I remember like there's 4 different X features in the iris dataset, and we can just get the prediction like loaded model.predict, and we can just give the new data point in here, and let's see our prediction. We got the class 0. Great. So we just saved our model as joblib file in here, then we loaded this model and we made a prediction with that. So think this like you can deploy this into a website. You can just send this to your machine learning operations team. They can deploy this on a mobile app, and customers or people in your company can use your machine learning models with this. Model persistence is essential when you have invested time and resources in the training a model and you want to deploy it in production or share it with others without the need to retrain. I have also videos like API deployment of machine learning models or creating web apps with Streamlit. You can check them for different types of deployment. Like in the Streamlit video, you are basically creating a website for your model and everyone can use your model from there. If you are into machine learning, I highly recommend that course. That was all for this video. Thanks for watching. I'm creating data science content and have more than 20 free courses in my channel. I'm also consistently sharing free data science projects. You can also check them from the playlists page of the channel. Thanks again for watching and have a great day.